Hello everyone, welcome to DP Tutorials by Donny Jirwa. In this teaching lesson, we will learn on one important topic, which is Oersted's experiment, which is the relationship for finding the relation between electricity and magnetism. Now it comes from one chapter from your syllabus, which is for studying the motion of charges and magnetism. Now what we have learned and what we have come across is that in our day-to-day life we will always have magnets, okay? And magnets might be permanent magnet or an artificial magnet. See, like for example, if I have a magnet in this form in which one end of the magnet will be one pole and the other end of the magnet will be another pole. This will be the north pole and this will be the south pole. Like if I have this magnetic compass, one end of the magnetic compass of the needle will be the north pole and the other end will be the south pole. The properties of this magnetic compass or magnetic needle will be in such a way that the north pole of the magnet will always seek the north pole of the earth, and the south pole of this magnetic compass or magnetic needle will seek the south pole of the earth. And apart from that, this magnet will also have magnetic field lines associated with it. So let these be the magnetic field lines produced by the magnet. These will be what? The magnetic field lines produced by the magnet. And if I have some, suppose these magnetic materials, okay, suppose in the form of iron nails, okay, all these iron nails will be what? When you bring these iron nails very close to the source of your magnetic field, they will be attracted by the magnet. And these iron nails, when they are being attracted by the magnet, we say that the iron nails are being magnetized. Okay, So what is being discovered? That there is a relationship between electricity and magnetism. Way back in the year 600 BC, even the Greeks also have discovered some naturally occurring stones or materials, by the name of magnetite. And these substances or these naturally occurring stones, which are nothing but compound of ferrous oxide, they are they show some kind of magnetic properties. Okay? They are naturally magnetic occurring substances available in nature, and they show magnetic properties, which means that if I bring some iron fillings, they will be attracted towards itself. But in reality, we have some of these materials such as iron, where we magnetize them, and then so that we will enhance the magnetic properties of that material. Okay, so all these examples which I have written over here, like for example, this is a bar magnet. A bar magnet is nothing, it is made of iron, and it is highly magnetized to the extent that it will have high value of magnetic properties. So in this particular context, we will learn about this Oersted's experiment. What did Oersted observe? When you look at this picture, this is the picture of a scientist by the name of Hans Christian Oersted. Okay, he found out that there is a relationship between electricity and magnetism, and he was so surprised to find out that in the year 1820, in the year 1820, he discovered this experiment which lays the foundation between the relationship between electricity and magnetism in the year 1820. In the year 1820, Hans Christian Oersted, he is a Danish physicist. That means he is from Netherlands. Danish are nothing but Netherlands. He did some experiment, and to his surprise, when he placed this magnetic compass on this circuit carrying current, or on the circuit carrying current, he found out that this magnetic compass shows a certain deflection. Okay, it shows a certain deflection, which means that if I have a wire carrying a current I, and if I bring this magnetic compass, if I bring the magnetic compass, which means this is the North Pole, you'll find out that this magnetic compass will one, it will show a certain deflection, which means that this is the compass, that means this magnetic needle will deflect towards different position. Okay? It will deflect towards different position. Like in this case, I have this circuit, and over here I have the cell, which means that one end of this battery will be positive and the other end will be the negative terminal. Okay, and I have a key. Okay, I have a key, and on this one-way key, suppose if I insert the plug, the moment I insert the plug, that means what will happen? Current will flow. Okay, current will flow through all the branches. Okay, it will flow through all the branches. Suppose if I name this end of the wire as NAB. Okay, as NAB. Suppose I name this as A, B, C, and D. The current will flow through all the branches of this circuit. And what happens before you pass current? Okay, before you pass current, or when you open the circuit, okay, when you open the circuit, current will not flow. Accordingly, in that case, when you take this magnetic needle, okay, this is your magnetic needle. When you take this magnetic compass, or when you take this magnetic needle, you'll find out that this magnetic needle will align along the direction of the Earth's magnetic field, which means that if I place this, that means for this end, north pole of the magnet will face towards one direction, and if I place another magnetic compass, okay, another magnetic compass on this region, which is along BC, that means it will point on this direction. And if I take this same magnetic compass and put it on the direction with respect to the other edge of the of the current carrying wire, that means this will deflect in, this will point on this direction, which is this is your original position. It means all these will be what? All these will be the original position of the magnetic needle. Okay, this will be the original position of the magnetic needle, which points along the direction of the Earth's magnetic field. So let me name this as position, the first position. Okay, the first position. This is what Oersted observed. Okay, this is what Oersted observed, okay, in his experiment. So this is your position number one. Okay, this is position number one, or view number one. So this is without passing current. The moment when I pass current, and when I bring this magnetic needle very near to this wire EB, very near to this wire BC, and very near to this wire CD, we found out, or Hans Christian Oersted, he observed that there is some kind of a deflection, which conveys and convince him that there is a magnetic properties associated with that current carrying wire. So from here, when I close the circuit by inserting the plug from this key K, okay, from that key K, what will happen? The current will flow. Okay? Current I will flow along that circuit. When this current I flows along the circuit, that means what will happen? This current along this direction EB, okay, there will be one current which flows along this wire EB. And originally, without current, the magnetic field, there will be no deflection on the magnetic compass, and this magnetic compass will point on this direction. But suddenly, when there is a flow of current, we find out that there is some kind of a deflection. There is some kind of a deflection. Okay? There is some kind of a deflection. And if I bring this magnetic compass, okay, if I bring this magnetic compass, it is evident that this magnetic compass will show what? Will show a certain deflection in such a way that this north pole of the magnet, okay, this north pole of the magnet will be deflected across this direction. Okay, it will be deflected across this direction. So I will tell you why the north pole of this magnet deflects along this direction, which means that this magnet, if this is the north pole of the magnet, that means this north pole of the magnet will deflect along this direction towards the right position. Okay, towards the right position, which means it gets deflected the moment when you place this magnetic compass very near to the current carrying wire. So let that be the second position. Okay, let this be the second position. Again, when current I moves across wire EB and then it moves across the wire BC, okay, originally the magnetic needle will be along this position number 1. But when you bring this magnetic compass very near to this wire BC, what happens? It so happens that this needle again will deflect. Okay? This needle again will deflect in one direction. So the way in which this needle deflects is that this north pole of the magnet will deflect along this direction. That means always towards the right side. Okay? Always towards the right side. And when I bring this magnetic compass, that means this magnetic needle, this north pole of the magnet, that north pole of the magnet always, this north pole of the magnet always deflects on certain direction. So I will represent in that direction. So this will be what? This will be the direction in which the magnetic compass has been deflected. So this will be the second position. Accordingly, when this current moves along this wire BC, again this current will move along the wire CD. Originally, when there is no current, the magnetic compass will point along the Earth's magnetic field. Now, when you bring this magnetic compass and when there is current flowing across this arm or branch CD, then this magnetic needle again will show what? Will show a certain deflection. Okay, it will show a certain deflection. So that will be what? That will be the position in which your magnetic compass will deflect. So in this case also, this north pole of the magnet will deflect in this direction, that means towards the right side. See, if I have magnet in this form, that means this will be the right side, that will be the left side. So it always deflect towards the right side. So from here, this will be the point in which the magnetic compass will show a certain deflection. So I can name these as what? As this will be the second position in which the magnetic compass shows deflection when current I is flowing through the wire. This will be also what? This will also be the second position in which when current I flows through that wire BC, indicating that even though if there is no magnetic field, there is no magnetic field on this wire, but still when you bring this magnetic needle very near to the wire itself, this magnetic compass shows a deflection. The deflected position, when the magnetic compass shows a certain deflection, it indicates that there is what? There is some kind of a repulsive force. Okay? There is some kind of a repulsive force. So this repulsive force, which is generated by the current carrying conductor, indicates that the current carrying wire produces a source of what? Produces a source of magnetic field lines, which means that over here, that means there will be what? Magnetic field lines associated with this, magnetic field lines associated with the wire, magnetic field lines associated with the wire, and this magnetic field lines associated with the wire will produce certain deflection on what? On this magnetic needle. Okay, so from here there are certain rules to find out the deflection of the magnetic needle. So from here I have drawn this figure. We will apply Ampere's law to find out the direction of deflection. Okay, the direction of deflection of our magnetic needle. So over here, this is your Ampere's law. Imagine that there is a wire. This is the wire. Okay, this will be the wire. This will be the wire carrying a current I. So this is the wire carrying a current I. So let this I be the current. So that I, this would represent what? This will represent the direction of flow of current. So the direction of flow of current is in such a way that this current enters the feet, okay, of the swimmer. You imagine that there's a swimmer which is swimming along the pool of current, and in such a way that if we have this conductor, and if I place this conductor, the current enters the feet and leaves his head. And we also know that there will be one will be the right hand and the one will be the left hand and the other will be the right hand. And if you keep this orientation, with respect to this conductor of BC, okay, you will find out that this deflection of the magnetic compass always tends to deflect towards what? Always tend to deflect along the position of the right hand or towards the right side of the swimmer. And if you take this swimmer again, and if you please, okay, okay, this is your left hand and this is your right hand, and if you swim along the direction of BC, the magnetic compass always will deflect across one, across the right side of your hand. Okay, so from here, which means that if I apply this Ampere's law is help for finding the direction of deflection of magnetic compass or magnetic needle. So the deflection of the magnetic compass would be in such a way that the north pole of the magnet, this is the north pole of the magnet, this north pole of the magnet always deflects towards the right side. Okay, always deflects towards the right side. So that is the way how to find the direction of your magnetic compass by applying what? By applying your Ampere's law. Okay, Ampere's law. So this is just an description of what we have explained. So what Oersted observed, okay, he found out that when he placed this magnetic compass near a current carrying conductor, what did he notice? He noticed that this needle of the magnetic compass shows what? Shows a certain deflection. And when this magnetic compass shows a certain deflection, it indicates that this current carrying wire also produces what? Also produces the magnetic field. And when it produces the magnetic field, this magnetic field produced by this wire opposes the magnetic field of this magnetic needle, which manifests itself in the form of what? Deflection, okay? Which opposes the magnetic field due to the compass, and that is why the compass one deflects. Whereas when there is no current, the compass will rearrange itself in the original position, which means that will orient in the north-south direction. Always the magnetic compass always will orient in the north-south direction, which is your direction of the Earth's magnetic field, always in normal position. Now for finding the direction of your magnetic field, or for finding the direction of deflection of the north pole of the compass, we use what? We use your Ampere's right hand rule. Okay, so this Ampere's right hand rule will be in such a way that if you imagine a swimmer, if you imagine the swimmer, and this swimmer swims in the direction. So over here I've written, if a swimmer swims along the direction of the current flow. So over here I have this wire, and this wire is moving in this direction in such a way that the current enters his one, in such a way that the current enters his field and leaves his hand. Okay, it enters his field and leaves his hand. Then the deflection of this magnetic compass, if I have this magnetic needle in this case, this north pole of the magnetic needle will always be towards what? Will always deflect towards the right hand. Okay, will always deflect towards the right hand. Again, if I have a magnetic needle and this is one, this is your north pole of the magnetic needle. This magnetic needle will always deflect towards what? This magnetic needle will always deflect towards the right side. So from here, if I draw, this needle will deflect towards this direction. So this will be the direction in which that magnetic compass will deflect towards what? Towards the right side. So this is your left side and this is your right side. This is your left side and this is your right side. So this magnetic compass always will deflect towards the right side. So in this position. So if you recall from here, that means if I have this magnetic needle in this position number 1, when the current is passing through that wire, then this north pole of the magnet, always will deflect towards the right side. Okay, always will deflect towards the right side. That is why this will be the orientation. And if you again recall with respect to this wire CD, this will be what? This will be your deflection. And if you swim along the direction of BC, that means this will be your direction. So from there, that will help you to find the direction. And in position 1, over here I've also written that position 1 indicates the normal position of the magnetic needle, and position 2 indicates what? the deflected position of the magnetic needle. Now, more illustration. And from here, in this illustration, we will have, okay, let us consider some wire which is moving, okay, in which let us consider a wire in which this is a current carrying wire, and there is a current I which flows, okay, which flows in the upward direction. This is the direction of your current flow. And another wire, let me reverse the direction of flow of current, and the direction of current is in the downward direction. Okay, so over here the current will be in the upward direction, and in this case the current will be in the downward direction. So from here, how will you find there will be magnetic field lines? Okay, there will be magnetic field lines associated with this wire. Okay, there will be magnetic field lines. That is why I have drawn the circular dotted circle. All these circular dotted circles are nothing but magnetic field lines. Okay, magnetic field lines. So from here, the direction of these magnetic field lines will be in such a way that it will be in this direction. So this will be the direction of your magnetic field line. So how can you apply that? We can apply that by using the right hand grip rule. Okay, if I use the right hand grip rule, the right hand grip rule will be in such a way that if I grab this conductor, and in such a way that this thumb indicates the direction of current flow. Okay, this thumb indicates the direction of current flow, and this curl of the fingers indicates the direction of your magnetic field lines. Like in this case, if the current is moving in the upward direction, so this will be your direction of your magnetic field. So that is why this direction of the magnetic field, in this case, it will be in the anti-clockwise direction. Okay, in this case, it will be in the anti-clockwise direction. So in this case, it will be in the direction of the magnetic field lines will be in the anti-clockwise direction by using the right hand grip rule. Now, when the current is moving in the downward direction, again, how will you find the direction of the magnetic field line? Use again your right hand grip rule. And when you use your right hand grip rule, and when this current is moving in this direction, this is the current I moving in the downward direction, then what will happen? This will be your direction of your magnetic field, and the direction of rotation of the magnetic field will be in the clockwise direction, which means that there will be, if I have only a single wire, that means there will be many magnetic field lines. There will be many circular magnetic field lines which are centered along this wire carrying a current I. So if this I is the current, that means from here this will be the direction of magnetic field lines. This will be the direction of your magnetic field lines in this direction. Okay, so the strength of the magnetic field lines also depends upon the distance from the center of the wire. If the strength of the magnetic field line very near to the wire will be more, and the strength of the magnetic field very far away from the wire will be less. So if I have this wire, and if this current is moving in the upward direction, so that current in the upward direction is always represented by a dot. Okay, it is always represented by a dot. So from here, let us represent by a dot. So this will be the direction in which the current, or you can imagine that the wire is perpendicular and into the outwards. Or if you consider in the case of the screen, that means this wire is out of the screen, okay, coming out. So when you focus in this case, that means if the current is moving outwards, okay, represented by this dot, okay, the current is moving outward of the screen or out of the page, that means this will be the direction of your flow of magnetic field line. So from here, if it is moving outwards, so this will be what? This will be the direction of magnetic field line will be in the anti-clockwise direction. So this will be your anti-clockwise direction. So from here, which means anti-clockwise direction, that means this will be the direction of what? Of your magnetic field. And when you place this magnetic compass, all these magnetic compass will align along this direction, which this will be the north pole, indicating what? Indicating the direction. This will be the north pole. This will be the north pole of that magnetic compass. This will be the north pole of that magnetic compass. This will be the north pole of that magnetic compass, and so on and so forth. So if the current is moving upwards, okay, if the current is moving upwards, that means this, okay, this will be the direction. Okay, if the current is moving upwards, so this will be the direction of what? Of your magnetic field line. This will be the direction of your magnetic field line, anti-clockwise. So anti-clockwise, that is why it is anti-clockwise. Okay, anti-clockwise. So represented by what? It is represented when the current is moving perpendicular and upwards, we represent by a dot. Now when the current is moving downwards, or imagine that the wire is moving, the current is moving in the wire, or in, if you adjust the wire in such a way that it is in the screen or into the page, that means it will move into the page or into the screen, okay, downwards. So it will be represented by what? It will be represented by cross. So this will be the direction of your current. So from here, what will happen? What will happen in this case? In this case, the direction, okay, the direction of current flow will be on the reverse direction. So this will be, that means this will be the direction. It will be in the clockwise rotation. So when it is in the clockwise rotation, that means this north pole, when you bring that magnetic needle, this north pole will be on this direction. It will move on that direction. It will move on this direction. So this will be the direction of what? This will be the direction of your magnetic field lines. Okay, this will be the direction of your magnetic field lines. So that will be the north pole of the magnet. The unshaded will be what? Will be the south pole of the magnet. In this case, the rotation is in this direction. The rotation will be on that direction. So in this case, the rotation will be on this direction. Okay, the rotation will be on that direction. Whereas in this case, the rotation will be in what? On this direction. This will be the rotation on this direction, which is in the clockwise direction. Clockwise direction. If the current is moving perpendicular and inwards, okay, perpendicular and inwards, or perpendicular and into the page, perpendicular and into the page. Now, if the current is moving perpendicular and upwards, that means this magnetic field will move on. The direction of the magnetic field will be in the anti-clockwise direction. So in this case, if the current is perpendicular and downwards, it is represented by what? It is represented by the cross. Yeah, this is your cross sign. And the direction of the magnetic field will be in this direction. This also you have to apply when you apply your right hand thumb rule. When you apply your right hand thumb rule, your curl of the finger will indicate what? Will indicate the direction of your see, if I use your right hand thumb rule, even at this case, the thumb will indicate the direction of your current into, so you'll find out this curls of the finger will always be in the clockwise direction. Again, if I take this same rule and apply over here, when the current is perpendicular and outwards, or this thumb it is outwards, okay, you'll find out that this curl of the fingers will be on this direction, which means that using the right hand grip rule or using the right hand thumb rule, we can find out what? We can find out the direction of your magnetic field lines. Okay, so that will be some of the important things that we need to know about the relationship between what? About the relationship of current, okay, of current and magnetism. Okay, so you just go through those lectures so that you will understand. Okay, so just go through those lectures so that you will understand the basic cases or the basic analysis of what we have learned. Okay, until we meet again, thank you.